Hello, in today's video I'll be discussing how to sample from language models. This is an elementary concept in understanding how large language models and chatbots generate their output, but it is crucial to understand. And to motivate this, I'm going to first present the subject of temperature, which you may or may not have heard of, and it is best presented, in my opinion, with such a graph. So you can see here that we have some hyperparameters and the resulting graphs. And what this is showing is that based on your temperature, what are the relative probabilities of sampling from the first, second, third, fourth most probable token when you are performing next token prediction on a transformer-based decoder. So what this means is that when you have temperature near zero, you are almost greedily sampling, such as taking the argmax over all tokens. And if you increase the temperature, then you are making it more and more uniform. So why is this the case? It's simply because the temperature is in the denominator and it divides all the logits. So when you have your final linear layer in a transformer, it will convert your residual stream into logits of dimension, the number of the vocabulary size. And this is then passed through a softmax function, which will give the probabilities. So if we want to make sure that the logit, which is the highest, will then convert to the highest probability in a argmax type of way, then we would need to make the temperature near zero such that it will be divided by near zero and tend towards infinity. And since whichever token has the highest logit will be the most favored by this division by zero, then it will, in the limit, be chosen with 100% likelihood. So essentially greedy selection. Whereas if you divide the logits all by infinity, then they'll all be zero. And then when you perform the softmax over a bunch of values which are the same, so near zero in essence, then every token will have the same probability, and that's why you can see purple is tending towards a uniform distribution, whereas blue is almost completely, all of the mass is on the first token prediction. So I just wanted to motivate that before we begin the discussion of sampling, because temperature is very important and it's used on many sampling algorithms to determine how much we favor the most probable token. Okay, now let's look at this graph. And the title is Beam Search Text is Less Surprising. And what we have here is time step on the x-axis. So here's the thing, time step, when you refer to a large language model, is the same thing as token step or sequence number. That is to say that time step 20 means the 20th token generated in a sequence. So just think of time step and sequence as analogous terms. And this graph shows that when a human performs next token prediction, it's much more stochastic, or not stochastic, but volatile in terms of the probability of next prediction. Whereas, of course, beam search, which in the limit where you only have one beam is just greedy selection, is much less surprising because you're essentially choosing whichever token has the highest probability at every time step. And this is why maximation-based decoding methods, such as beam search, lead to degeneration output text that is bland, incoherent, or repetitive, so getting stuck in a loop. And this is interesting because despite considerable advances in large language models, it's still debatable on what the best decoding strategy is for next token prediction, because we know that when we perform greedy selection, this gives us extremely undesirable results. And I have a Google Colab here, which I'll show you at the very end of the video, which will demonstrate the lack of diversity or blandness of this maximization regime. And you might ask, why doesn't it work? Because if we're performing next token prediction and we get a probability distribution at each new token, it would follow, perhaps naively or at least sensically, that performing the next token prediction on the highest probability should give good results. Here's the issue though. In training, there's never a chance for the model to see accumulating or compounding errors. What I mean is that the model is trained to predict the next token based on a human ground truth. This is to say, like if it's a Wikipedia article, what was written in that Wikipedia article. And let's suppose that at a specific time step or a specific sequence, the model gets the answer wrong. However, when it predicts the one after the wrong token, it still has the human prior, or rather, the incorrect prediction in the previous time step by the model is not propagated to the current one. Instead, we replace it with what the correct output was. However, during generation time, the model doesn't have the human prior to replace with any previous incorrect tokens. And instead, it must complete the next token prediction based on its automatically generated context. And this is why it's called the autoregressive model in passing. And therefore, in training, whereas we will replace any incorrect tokens with what the correct token was in the human text, in inference, when the model has been trained, it does not have this opportunity to just get rid of errors because it's generating new text. So there is no precedent to base off of. Now I can motivate the method, which is very promising, called in its original presentation in the paper nucleus sampling, or top P sampling. So top P sampling is the more common term. And in essence, it avoids what you would call the degeneration in decoding by truncating the unreliable tail of the probability distribution and sampling from the dynamic nucleus of tokens containing the vast majority of the probability mass. So let me explain this diagram you see in front of you, and then why does top P sampling improve on previous methods. So you can see here that we have two settings, so discrete and continuous. You may know this, but I just want to make sure we're on the same page. And for discrete, we have a probability mass function and a cumulative distribution function. So probability mass says for any given x, what is its probability? So this is a dice roll, if you couldn't tell, and every value has 1/6 probability. Whereas the cumulative distribution function says what is the probability of getting this value or less. So 1 is still 1/6, but 2 or 1 is 1/6 plus 1/6, which is 1/3. So it's just a cumulative version of the probability mass function. And then in the continuous case, which is what we consider in top P sampling, we have the probability density function. And the probability density function gives the probability density between any two values. So for example, the probability of being between 3 and 4 would be the probability density at 4 minus probability density at 3. And once again, the cumulative distribution function, which is the most important function for top P sampling. So if you didn't pay attention for other ones, pay attention to this one. This is saying if you have the say this is called function P of 4 is the probability of getting 4 or less. So this would be all of the mass under from here all the way to the left tail. So just keep this in mind. And I said that top P sampling or nucleus sampling truncates the unreliable tail of the probability distribution. And what I mean by this is that top K sampling, which is another well-known sampling technique in large language models, simply says that let's take the top 10 highest probability tokens. So now, if I switch here, you can see the problem it will be if you use top K sampling. And this is the fact that if you take, for example, the top 10 tokens, and you choose this example where we're predicting I ate the pizza while it was still blank, then because there's cooking, which is in the top 10 but still has very low probability, this is what you would call the unreliable tail, which can lead to deranged output. Notwithstanding, in top P sampling, we will accept tokens up to a specific probability mass. And a reference would be up to 90%. So we would accept in our cumulative distribution function, whatever x value gives us a probability, a cumulative distribution function equal to 0.9. And in this case, if hot is approximately 80%, then we can think that warm plus cooling would maybe equal 10%. So in this case, our top P probability will only be the first 3 tokens in this narrow distribution. And this avoids having these tokens from the unreliable tail. Whereas if you have a broad distribution, it still works as it should, which is to say, if there's a word all the way in the 10th position, which still has maybe probability of 6 or 7%, which is non-negligible, then we will still consider it as long as it's within our 90% threshold. But everything that is after the 90%, which can be thought of as perhaps extraneous, will not be considered. So this is the fundament behind top P sampling. So we compute the cumulative distribution and cut off as soon as the cumulative distribution function exceeds probability P. So we avoid sampling egregiously wrong tokens, but preserve variety when the highest scoring tokens have low confidence, which would be the example here with the broad distribution. And another way of thinking of it is as a dynamic version of top K sampling. So top K sampling, once again, the top 10 probabilities, it is undynamic because it's always 10 tokens. Whereas depending on the distribution, top P sampling might give you only 2 tokens if the first 2 tokens sum up to 90%, or it may give you 10 if each token is respectively worth 8% and you have a 80% probability cutoff. So this example shows very well the dynamic nature of top P sampling, as it is appropriate not only for narrow, but also for broad distributions, whereas top K sampling is weaker with narrow distributions because it may cause the model to pick tokens which should not be sampled. Okay, and before we finish this off, I have this collab here, which I will link in the video if you want to play with it. It's really simple. It just uses the Hugging Face Transformer interface API, and you can choose between greedy and top P sampling. There's also the number of tokens to be sampled, and you can give it the context. So I just set the context as a video about. So let's see what top P gives us. And top P should be more diverse and less bland, just to say very simply. So the top P sampling says it's a video about the man killed by police during a robbery on the northwest side, blah, 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 blah. Okay, as a member of the META, said Domenico. So it looks like it's an interview and somebody died in a police robbery. Okay, so that's pretty esoteric. And let's see what greedy gives us. So this is GPT-2. So greedy might still give us something that's relatively interesting. So let's see. A video about being one of the first ones to ever buy a Tesla Model X SUV released by car manufacturer General Motors in December 2015. Okay, Tesla Executive VP Dan Akerode offers a great list of good things. So this isn't rigorous at all in terms of this experiment, but I just wanted to show you the difference between greedy and top P. It seems that with greedy, we got some weird behavior with General Motors being equivalent to Tesla, which isn't true. Whereas in top P, we got a coherent output mentioning some robbery. I forget what it was exactly. And this is just to show you that greedy sampling is definitely not what you want to do. Either do top K or top P. Top P is my preferred sampling method in terms of the simple ones. Of course, there are many more methods that are out there. But if you're looking at the vanilla methods, top P is robust.